All right, quick question for you. What's the real difference between AI, machine learning, and deep learning? If you had to pause for even a second, you are in exactly the right place. Today, we're going to ace the AI technical interview, and we're not just going to talk about it, we're putting you right in the hot seat. I'll be your guide, your interviewer, walking you through all the key concepts you absolutely positively have to nail.
So just picture this. You're sitting in the interview. The hiring manager leans forward, and this is it. This is where it all starts. Can you prove you have a rock-solid grasp of the fundamentals? Ready? Let's get into it. First things first, we're cracking the core concepts. Look, before anyone asks you about the latest fancy model, a good interviewer needs to know one thing. Is your foundation solid? They're testing the B6, so let's prove to them that it is.
Okay, so this is one of the first and most common questions you'll get. And the best way to think about it is like one of those Russian nesting dolls. AI, artificial intelligence, that's the biggest doll. It's the whole grand idea of machines mimicking human intelligence. Then you pop it open, and inside you've got machine learning. That's the part that's all about systems learning directly from data. And then you open that one, and you find deep learning, which uses these really complex, multi-layered neural networks to do that learning. So remember, all deep learning is machine learning, and all machine learning is AI. Easy, right? So, how do these systems actually learn? Well, they really go down two main paths. With supervised learning, you're the teacher. You give the model a textbook full of examples that are already labeled. Thousands of pictures of dogs, each one labeled dog. On the other hand, you've got unsupervised learning. This is where you just dump a massive, messy pile of data in front of the model and say, go figure it out, find the patterns. This is awesome for discovering hidden structures in your data that you never even knew were there. Now, before you even start training a model, you have to set the rules of the game. That's where hyperparameters come in. Think of these as the knobs and dials on the machine that you, the engineer, get to tune. Things like the learning rate, how big of a step the model takes with each guess, or how many layers the network has. And here's the crucial part an interviewer wants to hear. The model does not learn these. You set them. Getting them right is part of your job. Okay, so your foundation is looking solid. The interviewer is nodding along. Now they want to see if you can actually build something. So let's get into the nitty-gritty, the mechanics of how a model actually learns. So at the very heart of pretty much all modern machine learning is this brilliant little algorithm called gradient descent. The best analogy is to imagine you're standing on a huge mountain, but you're in a complete fog, and you need to get to the lowest point in the valley. What would you do? You'd feel the ground around your feet to find which way is the steepest downhill. And you take one step in that direction. That is exactly what gradient descent does. It calculates its error, finds the direction to best reduce that error, and takes a tiny step. And it just does that over and over and over again, thousands of times, until it finds the bottom. But hold on, how does our hiker in the fog even know which way is down? Well, that's the job of the cost function. If gradient descent is the hiker, the cost function is the altimeter on their wrist, constantly telling them their altitude. It's just a function that spits out a single number that basically says, this is how wrong you are right now. The entire goal of training a model is to get that one number, that cost, as low as you possibly can. Okay, so in a really deep network with millions of connections, how does the error signal get to everyone who needs to learn from it? That's backpropagation. After the model makes a guess and calculates its error, backpropagation is like the manager walking the error report backward through the entire company, from the final product all the way to the first person on the assembly line. It tells every single neuron exactly how much it contributed to the final mistake, so each one knows precisely how to adjust. It's the engine that makes deep learning work. Now here's a little secret. Without activation functions, even a neural network 1,000 layers deep would just be a simple linear model. It could only learn to draw straight lines. Activation functions are the secret sauce. They're these little functions inside each neuron that add nonlinearity. They allow the network to bend, to curve, to learn the incredibly complex and messy patterns we see in the real world. Awesome, you've built a model, but guess what? It almost never works perfectly on the first go. So the next stage of the interview is all about troubleshooting. They want to know, are you a good detective? Can you figure out what's wrong with a model? And, more importantly, can you fix it? Okay, you are almost guaranteed to be asked about this. The bias-variance trade-off is one of the most classic, most fundamental concepts in all of machine learning. Why? Because it gets right to the heart of the main challenge we're always fighting, a constant tug of war between two different types of model error. And this perfectly lays out that balancing act. On one side, you have high bias, which we call underfitting. Think of this as a lazy model. It's just too simple, and it fails to learn the real patterns, even in the data it was trained on. On the complete opposite side, you have high variance, or overfitting. This is the model that tried too hard. It basically memorized the training data, including all the random noise, so it's brilliant on that specific data, but falls apart the second it sees something new. The whole game is finding that perfect sweet spot right in the middle. So since overfitting is such a huge and common problem, every good engineer needs a toolkit to fight it. And here are some of your best weapons. Regularization is kind of like putting a tax on complexity. It penalizes the model for getting too wild. Dropout is a cool trick where you randomly turn off parts of the network during training, forcing it to be more robust. And early stopping, that's just common sense, right? If your model stops getting better, just stop training. Now, when it comes to judging how good your model is, just saying it's 99% accurate can be really deceptive. We need to be more, precise. Let's think about a medical test. Precision asks, of all the patients we said have the disease, how many actually do? We don't want false causatives. Recall asks, of all the patients who really have the disease, how many did our test successfully find? We definitely don't want to miss anyone. But here's the catch. Usually, when you try to improve precision, your recall goes down, and vice versa. They're in this constant battle. So how do you find a good balance? That's exactly why we have the F1 score. It's a clever way to combine both precision and recall into a single score. It gives you a much more holistic view of your model's performance, especially when one type of error is way more costly than the other. Okay, you're killing it. You've shown you can build a model, you know how to debug it. Now comes the final technical part. The interviewer wants to know if you're up to speed. Do you know the state-of-the-art tools and architectures that are driving the AI revolution right now? A big part of being a great engineer is knowing you have to use the right tool for the right job. If your data is spatial, like an image, CNNs are king. Their convolutional layers act like little feature detectors, scanning across the image, looking for edges, textures, and shapes. But if your data is sequential, like words in a sentence or stock prices over time, you need a model with memory. That's what RNNs are built for, using their hidden state to remember what came before. And then the whole game changed. See, RNNs had to process a sentence one word at a time. It was a bottleneck. Then the transformer architecture came along and completely revolutionized everything. Its superpower is a mechanism called self-attention, which lets it look at the entire sentence all at once and figure out how every word relates to every other word. This parallel processing ability is what unlocked the massive power behind models like GPT and BERT. You know the saying, 2 heads are better than 1? Well, in machine learning, a few hundred heads are even better. That's the whole idea of ensemble learning. Instead of relying on one genius model, you combine the predictions of many simpler models. You've got things like random forests, which is basically a democracy of decision trees. And then you have absolute powerhouses like XGBoost, where each new model is built specifically to fix the mistakes of the one before it. These methods win competitions for a reason. They're just incredibly effective. All right, you've made it. This is the final boss of the interview. It's great that you can build an amazing model on your laptop, but here's the billion-dollar question. Can you make it work in the real world, reliably, at scale, serving millions of users? And this is absolutely crucial. A machine learning model isn't a piece of code you just finish and forget about. It's a living system that needs to be taken care of out in the wild. MLOps is the discipline of doing just that. It's about building the automated pipelines for testing, deploying, and most importantly, monitoring your models so they don't break down when the world inevitably changes. Because, let's be honest, the world is always changing. You'll run into data drift, which is when the data coming into your model today just looks different from the data you trained it on months ago. And you'll see model drift, where user behavior changes and your model's once accurate predictions start to get stale and wrong. The only real solution is a strong MLOps setup that constantly monitors for this drift and can automatically kick off a retraining job when it's needed. So after all that, how do you tie it all together into the perfect closing statement? You do it just like this. This answer is powerful because it connects all the dots. It goes from theory, like deep learning, all the way to real-world practice, like MLOps and scalable pipelines. It shows that you don't just know the definitions, you understand how to build real systems that create real value. And an answer like that leaves the interviewer thinking just one thing: how fast can we get this person an offer?